in this one there is a small correction for this test and set hardware instruction based critical section solution. There should be an instruction waiting I equal to false before the ith process enters the critical section. So this is the statement that I missed earlier. This is outside the while. Today we'll start a new topic, that is semaphore variables and applications of semaphore variables. Waiting I equal to false. This statement should come before the ith process enters the critical section. Okay. So now the full NT section will be initially waiting I equal to true. The ith process will set waiting I equal to true. Then its own local variable, that is key, that is also set to true. Then the ith process waits in the while loop, that while waiting I and key do key equal to test and set lock. When this while loop is broken, that is the ith process is going to enter the critical section. Before entering the critical section, it will set waiting I equal to false, then it will enter the critical section. So this new statement waiting I equal to false will come in the NT section. Okay. Otherwise there will be some problem, because here in the exit section we have said that if j equal to I, then lock equal to false. What we are trying to do is, if j equal to I, that means when the ith process comes out of the critical section, it is ensured that no other process is willing to enter the critical section. So ith process has come out of the critical section, no other process is willing to enter the critical section, that means I should go back to the initial state. And what was our initial state? Our initial state was all the elements of waiting, they were set to false, and Boolean variable lock, that was also set to false. Okay. So here what we are doing is, if j equal to I, then we are setting lock to false, but waiting I we are not changing. Okay. So that waiting I can be made false before entry to the critical section. So this will be part of the NT section. Okay. So today we are starting the topic on semaphore variables, and we'll see that how the semaphore variables and the operations on the semaphore variables can solve some of the operating system problems. Now, what is a semaphore variable? A semaphore variable is a special kind of integer variable which can be initialized and can be accessed only through two atomic operations. One is called a P operation and the other one is called a V operation. Okay. So a P operation is defined like this. If I define S to be a semaphore variable, okay, so the operations that I can do on S is, I can initialize the value of S, or I can operate this variable S only through two operations, PS and VS. Okay. So the PS operation, an operation on the semaphore variable, is like this. While S is less than or equal to 0, do skip S equal to S minus 1. Okay. So this is the PS operation. Similarly, VS operation is simply incrementing the semaphore variable by 1. Okay. So in PS operation, Firstly, the value of S will be checked. If the value of S is less than or equal to 0, then the process executing the PS operation will remain in the while loop. Only when the value of the semaphore variable S is greater than 0, it can come to the next statement and decrement the value of S by 1, then proceed with the other statements in the program. For VS operation, the value of S is simply incremented by 1. And we'll assume that both this PS operation and VS operation are atomic in nature. That means whenever a process is executing the PS statement, though you find that it is a combination of two statements, and the first one is a while statement. So if we want to break this into a number of assembly level language statements, you will find that this PS operation will be converted to a set of assembly language statements. Okay. But what we are assuming is that PS operation, similarly VS operation, both of them are atomic. That means when a process starts execution of PS or starts execution of VS, the process cannot be interrupted. Okay. Context switching can take place only after execution of PS or only after execution of VS. So once this starts execution of any of these statements, it has to complete that statement, PS or VS, and then only context switching can take place. Okay. So that is our basic assumption. Now let us see with such semaphore variables how we can implement say mutual exclusion problem. Okay. So what we'll do is, let us assume that we have a semaphore variable say mutex, which is of type semaphore. Okay. And we also assume that because we have said that the semaphore variable can be initialized, so let us assume that the initial value of mutex is equal to 1. So we initialize this mutex variable to a value 1. Okay. After that, we write the statements like this. First, you perform for every process, the process Pi, the statement will be first you perform P mutex, so only when P mutex is executed successfully, then only you enter the critical section. Okay. And in the exit section, you perform the operation V mutex. And then comes the remainder section of the program. Okay. So we follow the property of the semaphore variables, that is we can initialize it, or we can perform P operation on the semaphore variable, or we can perform V operation on the semaphore variable. Now you think of a situation that the ith process Pi, before entering the critical section, it executes P mutex. And what we do in P mutex, that while mutex is less than or equal to 0 do skip, then mutex will be decremented by 1. So our initial value of mutex is equal to 1. So if there are a number of processes who are executing similar kind of code and they want to share the same critical section, the first process which executes P mutex, that will find value of mutex equal to 1. Okay. So while loop will be broken because now value of the semaphore variable is greater than 0. Okay. So the first process, because while loop is broken, will decrement the value of mutex variable by 1. So value of mutex after execution of P mutex will be equal to 0. And the process enters the critical section. As long as the process is in the critical section, value of mutex remains 0. So if any other process wants to enter the critical section, that also has to perform this P mutex. Now while performing P mutex, the other process now finds that the value of mutex equal to 0. So again, following this while loop, that process has to remain in the while loop because value of the semaphore variable is equal to 0. So this condition is satisfied. So it will remain in the while loop. Okay. Now when that process will be able to enter the critical section? Only when the first process comes out of the critical section, performs v mutex operation. So when it performs v mutex operation, the value of mutex is incremented by 1. That is what we have done in Vs. Value of s is incremented by 1. So earlier value of mutex was 0. Now again it becomes 1. Okay. So the first process comes out of the critical section after setting the value of mutex to 1. When value of mutex becomes 1, it is the second process who was waiting in this while loop now finds that mutex has become greater than 0. So while loop will be broken. The process will decrement the value of mutex again by 1, making mutex equal to 0, and will enter the critical section. Okay. As long as this second process is in the critical section, value of mutex remains 0 because it can be made 1 only by the v mutex operation. And no other process can enter the critical section as long as value of mutex is equal to 0. Okay. And mutex will be made equal to 1 only by the process who is in the critical section, and while coming out of the critical section in the exit section, that will perform v mutex operation and will increment the value of mutex to 1. Okay. So you find that by simple strategy like this, following the property of semaphore variables, we can implement mutual exclusion solution. Okay. But again, as before, when we say that it's a critical section problem, the other two requirements are also to be satisfied, that is progress and bounded waiting. This does not ensure bounded waiting. Okay. So as we have done in our earlier cases, this only solves the mutual exclusion problem. So one of the requirement of critical section. To ensure that other requirements are also met, along with this we have to put some ornamentation that we have done same as what we have done earlier. Okay. So using the semaphore variables, we can implement mutual exclusion very easily. Let us see that what are the other applications of this semaphore variable. Semaphores are here. Among the other applications, the semaphore variable can also be used for process synchronization. Now, what do we mean by process synchronization? Say you come back to the precedence graph that we have said earlier. I can have a precedence graph something like this, that Pi has to precede another process Pj. Okay, that means the process Pj can be executed only after the execution of process Pi. Or let me use some other term. Instead of Pi and Pj, let me put them as Si and Sj to avoid the confusion between process Pi and the semaphore operation P. So suppose statement Sj can be executed only after completion of statement Si. So this is a synchronization problem. And you'll find that semaphore variables can also help to solve this synchronization problem. Here what we can do is, we can define a semaphore variable. Let us say that a semaphore variable sync. Sync is a semaphore variable and we initialize the value of this semaphore variable sync to, let us assume that it is initialized to a value 0. Okay. Then our statements can be something like this, that because sync is 0, initially 0, and we have said that PS operation we'll put the process in a while loop as long as the value of the semaphore variable is less than or equal to 0. Okay. We want Sj to be executed only after Si. So what we can do is, before execution of statement Sj, we can put a p-sync statement. Okay. So even if Si and Sj, they are to be executed by two concurrent processes, Sj cannot be executed until and unless value of sync becomes greater than 0. Okay. So before execution of Sj, I put statement psync. Sync can be made greater than 0 only by a vsync operation. So my sequence will be, I will first put Si and then vsync. Okay. This part may be executed by one process. This may be part of one process. This may be part of another process. Okay. These two processes can run concurrently. But these psync and vsync statements ensure that even if two processes are running concurrently, this Sj operation, Sj statement cannot be executed before the execution of Si of other process. Okay. So effectively what we have done is, though they are to be executed by two concurrent processes, we have serialized the execution of Si and Sj. Okay. And this is applicable in various parallel programming. For example, we have said that when we break the modules into concurrent modules, we have seen that we can break the modules into concurrent modules, submodules, only if the right set of one does not intersect with any other set of the other one. By application, by using this kind of semaphore variable, we can violate that condition. Okay. How we can violate that condition? Even if the right set of one intersects with the other one, but from the problem we have to identify that how some part of the statements are to be executed. Maybe a process consists of a number of statements. Many of them can be executed concurrently with some of the statements of another process. But at some point there should be some synchronization. That is where maybe a process 1 wants to have to get some input from another process to proceed further execution. Okay. So at that point, the first process which wants to have some input from the other process has to wait until and unless that input is ready from the other process. Okay. And there we can make use of such semaphore variables for process synchronization. Okay. So I can have situation like this. For a process say 1, I can have statements S1, S2 like this, statement say Si, then say Si plus 1, Si plus 2, and so on. For the other process, we can have statements say U1, U2 like this. Somewhere it will have a statement Uj, then Uj plus 1, Uj plus 2, and so on. Now what we need is that before execution of say statement Si of the first process, statement Uj of the second process must be complete. Okay. So here we are relaxing our concurrency condition in the sense that here we don't want that this entire process P1 has to wait for the completion, or let me put it as J1, this entire process J1 has to wait for the completion of process J2. Rather, we allow them to execute concurrently, but only will interrupt, will ask J1 to wait at the specific point when it needs the input from the process J2. Okay. So to enable this, what we can do is, here after uj, you put the vsync statement or vs statement, where s is the semaphore variable and the semaphore variable is initialized to 0, and before si you put the ps statement. Okay, so this ensures that up to si minus 1, the process J1 can work concurrently with J2. But when it comes to statement Si, it has to wait for process J2 to complete up to statement Uj. Okay. So after Uj of this is complete, then J1 gets the input. It can execute Si, and then for the remaining part, again J1 and J2 can be concurrent. Okay. So this way, even we can have partial concurrency among the processes, and this is what is known as synchronization problem. That is, at some point you synchronize the execution of two or more processes. Okay. This is another application of the semaphore variables. Okay. Now let us come back to an example that we had given earlier of a precedence graph. When we discussed about the concurrency problem, I had given you a precedence graph like this: S1, S2, S3, S4, S5, S6, S7. This was the precedence graph for which we had written a concurrent program using fork join construct. And that time we had mentioned that this precedence graph cannot be implemented, or this cannot be converted into a parallel code using co-begin coend construct. Okay. Now find that after introducing this synchronization mechanism by making use of the semaphore variables, even this precedence graph can also be implemented using co-begin coend construct. Okay. How you can do it? We can assume that each of these statements are to be executed by independent processes, and you synchronize the processes as required. Okay. So I'll have, how many processes I have? For S1, I have one process. So S1 will come under co-begin coend. Okay. What are the processes that depends upon the execution of S1? That is S2 and S3. So these are the two processes which can execute only after completion of execution of statement S1. So I have to incorporate some synchronization, and that synchronization I incorporate by making use of the semaphore variables. Okay. So let me use two semaphore variables at this point, say semaphore variable A and semaphore variable B. So after completion of S1, I'll perform VA operation. I'll also perform VB operation. While doing this, let us see how many semaphore variables we need. Okay. So I have VA and I'll have VB. Okay. Then S2, before execution of S2, I have to perform either PA or PB. Okay. So what I'll do is, I'll perform, let us assume the semaphore operation PA After PA, I have to execute S2. Okay. Now, this one says that S4 can be executed only after S2. Okay. So I can give, this is strictly sequential, right? So I can allocate this S4 to the same process which is executing S2. And within this statement, I'll put S4 after S2. Okay. So this says that S2 and S4 are to be executed sequentially, and this entire row will be under a begin end statement to ensure that within a row, the executions are sequential. We'll give you the complete structure later. And then what about S3? S3 also has to depend upon the execution of S1. I have one more semaphore variable left. Okay, so here I'll put PB and then S3. So statement S3 can be executed only after completion of statement S1. Okay, so I have finished S1, S2, S3 and S4. Then you find that execution of S5 depends upon the execution of S4. S6 depends upon the completion of S4 and S3. Okay, so I can have for S5, which has to execute after completion of S4. Okay, that means here I can put one more semaphore operation. Okay, and I'll put this as, say, V. Let me use some other semaphore, say VC. Okay, here I'll put a PC semaphore operation, and after that will come S5. Okay, so this ensures that S5 can be executed only after completion of S4. Come to S6, it has to wait for completion of S4 as well as completion of S3. Okay, so for S4, after this I need two semaphores. So one of them is VC, other one is, let me put as VD, where D is another semaphore variable. Okay, after S3, let me put semaphore VE. Okay, before execution of S6, it has to perform a PD operation, semaphore operation. It also has to perform a PE semaphore operation. Only after successful execution of PD and PE, statement S6 can be executed. Okay. Now come to S7. S7 can be executed only after completion of S5 and S6. Okay. So for S5, after S5, I have to put one V operation of semaphore. So I'll put it as VF. Okay. After S6, I have to put another semaphore operation. Let me put it as VG. Okay. So before execution of S7, the process has to execute PF and PG. Then only you can execute S7. Okay. I'll put all these under begin and end construct. So this will be begin, end. This will also be a begin, end. This will also be begin, end, begin, end, indicating that each row is a sequential process. Right? Now this whole thing, all these processes will be under co-begin, co-end, okay, and the parent process will be initiated by another begin end. Okay, and we have the semaphore variables. So the variables which are required are A, B, C, D, E, F, and G. All of them are of type semaphore and initialized to value 0. Right? So with this begin end, you start the parent process. Then the parent process says that it is co-begin co-end. When it says co-begin co-end, it knows that a number of child processes are to be created. How many child processes to be created? 1, 2, 3, 4, 5, and 6. So it will create 6 child processes. Every child process is sequential. So this child process will first execute S1, then VA, then VB. This child process is running concurrently with this, but it finds that the first statement it executes is PA. And since initial value of A is 0, until and unless S1 is complete, it will not execute VA operation. So unless VA is complete, this PA will not be successful. So though this process is running concurrently with this, but this is only waiting in the P statement for the completion of the P statement. Similarly, this process, though it is running concurrently with both of them, because all these processes are concurrent, this is also running concurrently with both of them. But since the first statement is PB, it cannot be successful until and unless this V operation is complete. That is because the variable B is initialized to 0. Okay, and that is true for all other. So you find that though each of them are running concurrently, but by imposing this synchronization mechanism through use of P operation and V operation of semaphore variables, I can have proper execution of this precedence graph. Okay. So you find that with the help of the implementation of semaphore variables with this P operation and V operation, this co-begin co-end construct is as powerful as fork join structure. Okay, so whatever precedence graph is given, you can now implement that both using fork join and also using co-begin co-end by making use of the semaphore variables and semaphore operations.
Is there any special reason for not declaring these variables inside the parent process?
Is there any special reason for not declaring these variables inside the parent process? Okay. You can declare this within the parent process also. There is no problem. Because all these semaphore variables are accessed only within this. So for this particular application, you can declare it with the after begin statement as well. So for this particular application, it won't give any problem. But there may be situations, because child processes share the variables of the parent processes. So if there is a situation that for different child processes, the parent processes are also different, then you have to take care that in which particular instance the variables are to be declared. In this particular application, I can simply shift it from here to this location after begin statement. So for this one, it won't give any problem. Right? Now find that in this semaphore variables, the two operations that we perform, that is PS operation and VS operation, we have seen that PS operation will be successful only if the value of the semaphore variable is greater than 0. Right? And in this example, as we said, that we have 6 processes. The 6 processes are running concurrently. That means all these processes are in the ready state. Okay. The CPU scheduler takes one process after the other, one after another, and gives that to the CPU for execution. Okay. Now, when say this process is given to the CPU for execution or this process is given to the CPU for execution, and if I assume that when these are executed till that time execution of S1 is not complete, that means both these processes will execute in the while loop of P operation. Okay. So these processes are executed only to be executed in the while loop without giving any fruitful result. So it is consuming the CPU time without giving any positive result. So this is a problem which is known as busy waiting problem. It is keeping the CPU busy for performing no positive work. Okay. So we have to think that how this busy waiting problem can be reduced. Okay. So that can be done by modifying the semaphore structure and by redefining the semaphore operations. Okay. Now in this modified semaphore definition, earlier our definition of semaphore operation was semaphore variables was that it's a special kind of integer variable which can be initialized and can be accessed only through P and V operations. Okay. So that means the semaphore variable was a scalar quantity having only integer value. Now instead of using semaphore variable only as an integer variable, we define the semaphore to be a structure or a record having two fields. One field will contain the integer value, the other field is a list waiting for that semaphore variable. See, what is this P operation? This P operation is nothing but I can have a number of processes which will perform P operation on the same semaphore variable. One of the processes will be successful who finds that the value of the semaphore variable is greater than 0. The other processes will remain in the while loop in the P operation of that semaphore variable to wait until and unless the value of the semaphore variable some value of the semaphore variable becomes greater than 0. So we can otherwise say that all those processes are waiting for that semaphore variable to be free. I can put in this term also. Okay. So if I redefine the structure of the semaphore variable, now semaphore variable will have two fields. One is the integer, that is the value of the semaphore variable, and the other field is a list. It is the list of processes who are waiting for that semaphore variable to be free. Okay. So now the semaphore variable will be defined like this. We can define it this way. I can define a type semaphore. See, all this language structure we are using is Pascal convention. Okay. So we define a type, and this kind of type is called an enumerated type or user defined type. Okay. So I define type semaphore as a record. Okay. This record will have two fields. One is the value field, and the value field is of type integer. Earlier the semaphore was having only integer value. Now it is a record. A component in that record is an integer value, and the second one is a value, say L, which is a list of processes. Okay, and that ends this type declaration. Okay. Now with this, whenever I define a variable S to be of type semaphore, say variable S, whenever I declare a variable S to be of type semaphore, that means this variable S is a record having two fields, value field and L field. The value part of S will be accessed as s dot value, okay, and the list part of s will be accessed as s dot l. This is typical structure definition or typical record definition. In case of C, we call it structure. In case of Pascal, we call it record. So we are following the same convention. And now we redefine the PS and VS operation. We define PS operation as, firstly, in PS operation, the value of the semaphore variable is to be decremented by 1. So first you decrement s dot value to s dot value minus 1. Okay. Then you check what is the value. So we put if s dot value is less than 0, then begin add this process to s dot l. Okay, you add the process to the list of the semaphore variable, and after adding the process to the list, you block the process. So this blocking is equivalent to putting the process into wait state. So you know that as long as the process is in the wait state, it will not consume any CPU time. Only the processes which are there in the ready state, they will consume CPU time. Okay. So since the process which finds that s dot value is less than 0, that is put into s dot l, the list of semaphore variable l, and that is blocked or put into the wait state. So the process, once it is in the wait state, it cannot wake up by itself. So I must have some mechanism which will remove the process from s dot l and wake it up. That means it will put the process from the wait state back into the ready state. So once it goes into the ready state, it will compete for the CPU time. Of course, it does not mean that the moment the process goes to ready state, immediately it will be executed by the CPU. It only means that it is now competing for the CPU time. Now the CPU scheduler will decide when the process will be executed by the CPU. Okay. So this is our redefinition of the PS operation. Similarly, we can redefine the VS operation like this. Firstly, s dot value has to be incremented by 1, so it will become s dot value plus 1. Okay, so that is the reverse of this. In PS operation, we have decremented the value by 1. In VS operation, we have incremented the value by 1. Then, if s dot value is less than or equal to 0, then begin remove a process P from s dot l. Okay, so VS operation, while performing VS, firstly it has to increment the value by 1. After that, it will remove one process from the list of processes waiting on semaphore variable s. Okay, so this may depend upon whichever is at the header of the list that will be removed by VS operation. After removing the process, it has to wake up P. That means earlier the process was in waiting state. This wake up means it will change the state of the process which has been removed from s.l from waiting to ready. So it will be put from the waiting state, removed from the waiting state, and put into the ready queue. Okay, and then finally end. So you find that the PS operation is blocking a process, and once the process is blocked, the process cannot wake up itself by itself. So that is the responsibility of removing the process from the waiting queue, and to put it into the ready queue will be the responsibility of a process which executes VS operation. And these two processes are different. As we have seen in case of our critical section problem, that to decide which process will enter the critical section next, that is decided in the exit section of the process which is coming out of the critical section. Okay. So that is decided in the exit section. That means which process will execute will be entering the critical section next is decided by some other process. Similarly here, which process will go to the ready queue, okay, out of the processes which are put into s.l, that is decided by a process which executes VS statement. It is not executed, it is not decided by the same process. It is decided by other process who is executing VS statement. Okay. So here you find that if we initialize s dot value to 1, the first process will execute PS statement, decrement the value by 1, that means value becomes equal to 0. Since value is not less than 0, immediately it will enter the critical section. Right? The next process who wants to enter the critical section, that will decrement the value by 1 again. Now it becomes less than 0. So the first process is in the critical section. The second process, which finds s dot value is less than 0, that goes to the list of s, and that is blocked. And it will wake up only when the first process comes out of the critical section and executes VS statement. When it executes VS statement, it sets the value to, restores the value to 1, then removes the process which is in the s.l and puts that into ready queue. Okay, and subsequently the process which is put into the ready queue, that will enter the critical section. Okay, so here you find that we have been able to avoid the busy waiting, because as long as the process is waiting for semaphore variable s to be free, it is not consuming any CPU time because it is blocked. It has been put into the waiting queue. It is not there in the ready queue, which was not there earlier.